Hello! In this video, we are going to prove the following theorem. Suppose G is a group and A is an element of G. Then for all integers n greater than or equal to 0, the inverse of the element A to the n is equal to the inverse of A raised to the power of n. Now, since G is a group, this means that G is equipped with a binary operation. G is closed under that binary operation. Associativity holds. G has an identity element, and every element of G has an inverse. Now, we define exponentiation for elements in a group as follows. Given a group G with identity element E, and given A is an element of G, then for each integer n greater than or equal to 0, we define the element A to the n as follows. A to the 0 is the identity element. A to the n plus 1 is equal to A to the n times A for all integers n greater than or equal to 0. So we've defined exponentiation for integer exponents greater than or equal to 0. And the notation that we've been using for inverse elements looks like an exponent of -1, but we haven't defined negative integer exponents yet. When we do define negative integer exponents, we're going to show that the notation that we've been using for inverse elements is unambiguous with an integer exponent of -1. But for now, we're going to treat this as a superscript of -1, right? It's not an exponent of -1, right? It's just the notation that we're using for the inverse of an element. Now, in proving this theorem, we're also going to be using the following preliminary results. Given any group element A, we have that A to the m times A to the n is equal to A to the m plus n for all integers m and n greater than or equal to 0. And given any two group elements A and B, the inverse of AB is equal to the inverse of B times the inverse of A. Okay, so now let's get into proving this theorem. Now to start with the proof, let's let G be a group with identity element E, and let's let A be an element of G. From here, we want to show for all integers n greater than or equal to 0, this equality is true. And we're going to show that using induction. So let's start with the base case. In the base case, we're trying to show that this is true in the case where n is equal to 0. In other words, we want to show that the inverse of the element A to the 0 is equal to the inverse of A raised to the power of 0. So let's start out by writing the left-hand side. Now, we know that A to the power of 0 is equal to the identity element. But then, the inverse of the identity element is equal to the identity element, because if we recall from the definition of the identity element, we know that the identity times the identity is equal to the identity, and we know by definition of the inverse of an element, the identity times its inverse is equal to the identity as well. Therefore, we can set these guys equal to each other, and by the cancellation law for groups, this implies that the identity is equal to the inverse of the identity. Alternatively, you could use the fact that the inverse of an element is unique, and so this immediately implies that the identity is equal to its inverse. So yeah, this is why we get this. But then, we know that any group element to the power of 0 is equal to the identity element. So not only is A to the 0 equal to the identity element, but the inverse of A to the power of 0 is equal to the identity element. And so, through this chain of equalities, we have shown that these two guys are equal. So this completes the base case. Now, let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 0, and we assume that this equality is true for that arbitrary integer n greater than or equal to 0. And the whole goal of the induction step is to show that this equality is also true for n plus 1. In other words, we want to show that the inverse of the element A to the n plus 1 is equal to the inverse of A to the power of n plus 1. So let's start out by writing the left-hand side. Now, we know that n plus 1 is equal to 1 plus n. And by this result, if we take m to be 1 and n to be n, well then a to the 1 times a to the n is equal to a to the 1 plus n. So we get this. But then a to the 1 is equal to a, because according to the definition, a to the 1 is equal to a to the 0 times a, but a to the 0 is equal to the identity. So this is just the identity times a, which is equal to a by definition of the identity. So a to the 1 is equal to a. And then, applying this result, we're going to take a to be a, and we're going to take b to be a to the n. Well then in that case, the inverse of a times a to the n is equal to the inverse of a to the n times the inverse of a. But then, by the induction hypothesis, we know that this guy is equal to this guy. But then, applying the definition, if we replace a with the inverse of a, then we have inverse of a to the power of n times inverse of a is equal to the inverse of a to the power of n plus 1. And so through this chain of equalities, we have shown that these two guys are equal. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. And so by mathematical induction, we have shown for all integers n greater than or equal to 0, this equality is true. And so this completes the proof. And so yeah, that's pretty much it for this video.